So basically, this is the best part actually. So because we started from the concept just capturing, we wanted to capture the variance of the data. So find this axis along to which if we project everything, we preserve the largest amount of information about the data. So the goal was to find a vector, u1, such that when projecting the data x onto u1, we capture its maximum variance. So this is the basic idea. And here I'm talking about a very simple case. We're going from 2 features to 1 feature, okay? We were extracting only 1 feature, and then we're going to generalize mathematically. But all the math that I will develop here, walk you through it briefly, okay? It's just, we're just looking for the first component, for the first projection axis, okay? Now, how to do that? So the idea is like we have a matrix X. We want to find our projection vector or direction u1, okay? And its dimensionality is d, okay? So we have it's d times 1, and then we're going to get a vector, a projected data point on u1 with the same dimensionality. So here what we're doing so far, we're just projecting, right? We're not reducing. We're just trying to find the u1. We want to find this guy. We don't know where it is. It can be anywhere in the space. That's what we want to find. We want to find our u1. So how to formalize that? So the first thing is, to find this u1, we need to maximize this variance. So if you guys remember, optimization, machine learning is all about finding the optimum, whether it's a maximum or a minimum. So we're going to formalize it as a learning problem, okay, to solve, as a optimization problem. Now the optimization problem, what we want to do, we want to find the u1 vector, okay, the first component, like the direction, u1, along which if we were to project, so this is the projection, project, the data onto u1, we will maximize its variance, okay? So this is the u1 vector that achieves the maximum variance of the projected data. Projected data, which means we want the maximum variance of this guy, okay? So here, projected data. Okay, cool. So next, to do that, so we define the variance of xu1. So here, this is a very interesting thing. So it turns out that the variance, okay, of xu1, this variance is defined as u1 transpose times the covariance matrix of x times u1, okay? So this is the covariance matrix of the data x, and I can normalize it here, so just to make things right. So why we found this? So I'm going to just give you a hint, but what you guys need to remember, if the variance of x projected onto u1 is exactly equal to this quadratic form, okay, where we're taking u1 transpose covariance of the matrix of the data x times u1. So this is, mathematical definition, and there is a proof of this. So how did we get that? So let's look at this. I'm just going to go over those. What is the total variance of a data set? So question number 1, what is the total variance of a data set X belonging to ND? So how we define it, if you guys remember, just the variance of, if we have the covariance matrix, let me just write it. If we have the covariance matrix, the total variance of this data, we know that all what is on the diagonal is the variance, okay? So this is a D by D matrix. So the total variance of my data is the sum, okay, of all the elements on the diagonal, which are just the variances of each feature. So this is the variance of feature 1, 2, 3, etc. until we get the D feature. So summing, if you remember in linear algebra, summing the elements of a matrix is the trace of a matrix, okay? So this is basically the total variance of X is the trace of the data covariance matrix sigma, and this is how we define it. It's just summing over all features from 1 to D of sigma I. Okay, so these are the diagonal elements. So here what we have, I and I. Okay, great. So next, what is the total variance? Now this is the question. What is the total variance of projected data set? So if we were to project the data. So this is the question that we want to find. So here we want to find the variance of the projected data right there, okay? So if V denotes basically a projection vector, what we need to do, the projected variance, we simply replace the x by its projection. So this is basically what we have earlier is, if you guys remember, if it's x, so this is the covariance. Let me just write it down. So here, this is the covariance, and what we're doing is basically first we're computing the projected variance. We're projecting xi, sample xi, onto a vector v. So this can be written as that, okay? So each xi, I'm gonna replace it. Each sample, I will replace it with its projected sample, okay, onto the new vector, onto a vector v. This is the general formalization. So if I do that, okay, then what I will get this. So so here, because it's a transpose, you guys know if I transpose this, I'm gonna get basically xi transpose v. So this is just linear algebra. And then just, you know, dividing this by the number of samples. And if I group everything together, because v is a constant, I'm not looping over v. So v is a constant, so I can just put it out of the sum over all samples I. And what I get next is this. So the variance of xv is basically vt covariance of x v. So this is exactly this, right? So this is what I was talking about. How did we get this one? Okay, so this is how we got it right here. So if I want to maximize the variance, okay, of x as projected onto v, okay, the variance of the projected data onto v, I need to maximize basically exactly this quantity, which is vt covariance times v. Okay, you guys got that. Now let's go next. So this is our new optimization problem. So the new optimization problem, we want to maximize, find the best U1 that maximizes the variance of the projected data onto axis U1. Okay, now what is most important here? Is it the direction of the projection or the magnitude? Okay, think about it. So what is the magnitude? Magnitude of the vector U1, okay? So here, if I want to maximize the variance of the data, all I need to find is this axis, right? I don't care if it's a long vector or it's a short vector. I don't care if this is my U1 or this is my U1. All I want to know is this is my direction. I can now project all the points on this axis. So if I know the direction, that's all I need, okay? Now there's a problem. If I only focus on the direction, what happens? If I want to maximize this, okay? What is the most trivial solution? Trivial solution. I can make U1, the norm of U1, tend to infinity, increase the values infinitely, right? Make them explode. So then this quantity will increase, right? This is a problem. So what we need to add a constraint. We need to say, okay, I don't care if the norm of my U1 is equal to 1 or 2 or 3 or like a constant, but I want to constrain it, because if I don't constrain it to be fixed, then the algorithm will try to just boost the norm of U1 instead of the direction. It doesn't care. So I can choose this direction, and it's wrong, and make the norm of U1 go to almost infinity, and I've maximized this, right? So that's not good. So we need a constraint optimization. So to do that, we need to add a constraint. So here we selected unit vector, but we can select anything basically. It's just we need to constrain the problem to avoid the trivial solution. Now, this is a maximization problem. Guys, you can take it from here and you can solve it step by step. What is the next step? So we have a function. This is our cost function that we want to maximize, okay, f, under the constraint g equals c. So what is the next step? Define what? The Lagrangian, right? So the Lagrangian, and what we want, we have a variable. This is our primary variable. We can define a lambda Lagrangian multiplier, and it's basically f minus g minus the constraint. Okay, if you guys remember, this is the right way of doing it. Let's look at this very quickly. So 2 more minutes. So here what we have, this is the Lagrangian. And this is my condition. So this is the norm of u minus the constant, okay? And this is the Lagrangian multiplier, the lambda. And then what we need to do next is solve the primal problem. So it's quite simple. Now this is the magical part where everything will fall into place. So if we solve this, let's derive it using these two rules. So I gave you the rules. You guys gonna take a minute and write it down. What is the derivation of the Lagrangian with respect to our vector that we're looking for? And anyone tells me very quickly. But 2? Yes? Minus lambda minus 2 lambda u1. Okay, good. Now we set it to 0. If we set it to 0, what do we get? Let's see. So we get, remove the 2's, so we have sigma u1 equals lambda u1. And this is exactly the definition of an eigenvector and an eigenvalue. An eigenvector, if you multiply it by a matrix sigma, right, you get exactly the same vector, just, multiplied by a coefficient. So this is the definition, the simple mathematical definition of an eigenvector of a matrix A. So an eigenvector of matrix A, if we have AX equals lambda X, it means that this is an eigenvector of matrix X, and this is its associated eigenvalue. Okay. Now we see that our U1 should be an eigenvector of the covariance matrix. We discovered that, guys. Okay. Now the next step, the dual problem. How are we going to do that? What is the next step? Remember, we take the constraints. What did we find? We find sigma U1 equals lambda U1. This is what we got from the primal problem. We need to plug it into the Lagrangian. Okay? Update the Lagrangian and maximize it. So, if we plug it in, what do we say? What do we find? We find sigma U1 equals what? So if let me just write it down. So here, this is the original Lagrangian. U1 transpose sigma U1 minus lambda U1 transpose U1 minus 1. So here, basically, I replace the sigma U1 with lambda U1. So I get lambda U1 transpose U1. And then minus lambda U1 transpose U1 plus lambda. Okay, so this disappears. And then I have the Lagrangian, the dual Lagrangian is equal to lambda. And what is the next step? Is to maximize the dual Lagrangian, right, over the Lagrangian parameter. So we need to maximize what? Lambda. So this is why we need to pick the highest, the largest eigenvalue, because we need to, this is the lambda one corresponding to the U1. It's, it should be the maximum eigenvalue, okay? Now you guys see that how all of this falls into place.